Hi guys, welcome back to the channel. In this video we are going to discuss serial in serial out shift register. So let's get started. In the previous video of introduction to the shift registers, we have already discussed about the loading and the retrieving the data. So in the loading data we have two types of loading. One is serial loading and one is parallel loading. Both of them requires 4 clock cycles. And retrieving data also has two methods, that is serial out, parallel out. But based on those 4 types, we are going to have the 4 categories. These are all 4 categories. In this video, we are just focusing on first one. That is serial in, serial out. Shortcut we can call it as SISO, SISO. The main motto of the thing that you can understand from the heading itself or the title itself, that is serial in, serial out. So the basically inputs will come as serial. So the each box represent each flip-flop, and serial out means the last out flip-flop's output is going out in a serial out manner. So this requires 4 clock cycles, all the 4 bits to the 4 flip-flops, and it requires 4 clock cycles to retrieve all the output, means in the serial manner. So now you might get a doubt, why we are going in the right side manner? We can also go the left side. Yeah, it is also possible. If you are moving towards right side, all the bits are shifting to the right side. It is known as shift right shift register. So basically this is SISO only, but in SISO we have two types. One is shift right, one is shift left. That is shift left shift register. Basically it will start right side and it moves to the left side. So that you can see over there that just exactly opposite of the shift right. This also requires to be 4 cycles to be gone inside and 4 cycles to come out. And the data will move from each flip-flop to each flip-flop one by one, as you're seeing in the blue arrow indicated in that. Now we are going to understand the 4-bit SISO shift right shift register. So first of all we are going to understand the right shift. So this is the basic right shift register that you can see over there. Total we have 4 D flip-flops attached in a fashion, that is D3 is our MSB and D0 is our LSB. So basically we are using D flip-flops because it is very convenient to use. So whatever, if you pass the input, that becomes our output. So that is why it is convenient to use D flip-flops. And clock is synchronized with the all flip-flops. So this is synchronous circuit. And input we are passing first MSB, that is D3, and remaining all things are inputs are previous outputs only. You can see over there all are attached to previous flip-flops. Now we are going to construct the truth table so that you can understand the behavior or the function of this shift register or how it is shifting towards the right. So let's start that. Now we are going to have in the shift register outputs as 1010. So we are going to start pushing into the flip-flop as 0. So before that I am taking the clock as 0. You can see in the truth table. So if clock is 0, anything may be the input, but outputs will be 0. This is our first condition. The next thing would be clock is high, then input is 0. Suppose the required thing is 1010. So first of all we need to push the input as 0. So you can observe that the Q3 becomes 0, Q means the extra 0, the new 0 that is. And remaining all things would be pushed. The place at Q0 is popped out. All the things are moved forward. You can see in the truth table that with the indicated arrows also. All the things are moving, how it is moving or how they are shifting towards right. So the next thing in our required thing is that is 1010 right. We have already pushed the 0. That is LSB. Next thing that we are going to push is 1. So you can have the input as 1, then you can move all the things. So you can see the 0 is moving to the next and the present input Q3 becomes the 1. And again at the Q0 position we are going to pop out the previous 0 and that is new 0 become the right shift. The next thing in our required thing is 0. So that is the button of MSB. So again you are going to push 0. You can also observe that again the red 0 is shifting towards right and the 1 is also shifting. The new 0 is inserted in Q3 position and again Q0 position is popped out. If you see, when clock is high, in the last thing that required MSB as 1. So you are going to push that one in the MSB position. So that Q3 becomes 1, all the things would be shifted towards right. The final thing is required thing, that is 1010 is obtained at all output positions. You can also see the timing diagram analysis so that you can get more clear about that. So the same thing that I have drawn in the timing diagram analysis. So keep the truth table aside and you are going to draw the truth table. You are going to draw with the help of truth table the circuit diagram also. So the first of all we are going to draw the input. So if you see the input, that is 0 1 0 1. So according to that I am going to draw the input. So first 0, then high, then low, then high, then again low, because that is our required thing. So according to that, draw the clock also. So now you are going to draw the Q3, that is 0 1 0 1. So according to that, according to input we are going to draw the Q3. So according to the Q3 we are going to draw again the Q2 also. If you see the Q2 in the truth table, so that is only one in one position, that is in the third position. So draw that only one. So Q1 only one we have in the last position. So draw that. So Q0 it doesn't have any ones. So that is plain. All the levels are 0 in the Q0. You can also verify by putting all the things with zeros and ones. Then you can see in the last position we have obtained 1 0 1 0. That is our required thing that we are pushing on the inputs. That what we have pushed the inputs into the flip-flops. And one thing, if you see the last case, that is for retrieving the data, we have directly Q3, but we are going to have the retrieve data with the help of Q2 by shifting Q1 one shifting, Q0 one shifting. So retrieve data we are going to have the 3 clock pulses. And in general situation for n bit SISO shift register, we are going to retrieve the data in n-1 clock pulses are required. Because we already have the MSB, but we need to retrieve the data before that n-1 times we are going to have or pass the clock pulse to retrieve the data excluding the MSB. And one more important thing in this right shift register, that is the input after each clock pulse should be controlled. So if not controlled, otherwise some random inputs will be inserted. For that we will modify the circuit. So I hope you understood from this statement that if you doesn't control the input, so first of all we are inserting 1 0 1 0 in the previous situation. So if you not controlled after inserting the first 0, again the inputs might be inserted random things, so that we don't want. So for that purpose only we are going to modify the circuit and we are going to control the inputs. So we have a control over the inputs, so that we are going to have the perfect outputs. So let's see the modified circuit. So this is the modified circuit. If you watch our previous video, it is somewhat similar to that. So we have enable bar, enable. So input we had only one input. So in this shift register only we are going to perform the shift right thing. So if you confused with this circuit diagram, no worry, I will explain now itself. So if enable is 1, we are going to have the right shift, and enable is 0, we are going to retain the previous outputs only. So the first situation is when enable is 1, we are going to have the shift right. So how the shift right happens? So if you see directly the blue highlighted AND gates, the first blue highlighted AND gate, starting with their input is going to the first D3 flip flop. Then again it is traversing to the D2 flip flop. Again it is traversing to D1. Like that again it is traversing to D0. Like that the right shift would be happening when enable is 1. In the same fashion, if you observe, when enable is 0, the resistor will retain its previous outputs. So what is meant by that? So if you observe, when enable is 0, the current input, the new input is not going into the flip-flop. So that is the reason. Or if you observe, the Q3 input is again feedback to the same thing, D as D3. And Q2 is again feedback to the D2, Q1 as D1, Q0 as D0. So we can say we have just feedbacks. So the previous outputs are retained, we can simply say from that. So basically if you observe, the two AND gates will be joined with the OR gate is nothing but 2x1 multiplexer, and we have a selection line here. So here enable line is directly given as selected line, and 1 as input for the first 2x1 multiplexer, and 0 is connected to the next flip flops 1. So it is almost similar, and you can relate with the circuit diagram previous thing, because both the things are same. In this we have just represented as block diagram. Block diagram is nothing but 2x1 multiplexer. In the previous thing we have discussed with the expanded thing, that is with the AND gate and OR gates. Just that is this is the simple version of that. If you have the enable line or the select line as 1, we can have the right shift. Or if you have the enable line or the select line as 0, we can have the previous states as retained. So if you observe clearly, we have that only. When enable is 1 or the select line is 1, we are going to have the right shift. So you can observe, you can relate with the normal circuit diagram also. First, if you have the enable 1, here in the 2x1 multiplexer, we are going to select the line 1. So what is the line 1? That is inputs. So input will enter the D3, again it will pass to the second flip-flop D2, like that it will going to pass. The remaining thing would be also be the same. So the next thing that we are going to see is the 4-bit SISO shift left shift register. Means this is left shift register. So up to now what we have saw, that is right shift. This is left shift. There is nothing but just a small change, that's it. So just invert all of them, that becomes our left shift register. So observe clearly, in this we are going to have for LSB as D0, MSB as D3, and we are going to input from D0 and take output from D0, and just invert the clock pulse. We are going to start clock from D0 and end at D3, like this we are going to go. And the truth table would also be the same, the insertion would also be the same. So in this, for example, I am going to insert 1100. So if you observe clock, input Q3, Q2, Q1, Q0 I had. So just start inserting from the left side, that's it, and move towards the left side. Sorry, that is the right side. Means start inserting from the right side and move towards the left side. So this is the left shift register. So we have something called 4-bit bidirectional SISO shift register. So with the help of the single circuit, we can perform both the left shift and right shift. You can see over there we have two inputs. So the left one, that is input RS, means right shift. So the right one, that is, so the left one, that is input LS, means the left shift. And we have the enable line, that is R.L. So you can have the right shift or left shift according to your inputs. So first of all, if you observe, if you pass the RL, that is enable line as 1, you are going to perform the shift right. In the same way you can observe that you are going to start from the left side and slowly move towards the right side. So that is known as shift right. You can also observe the connections how I gave. In the same manner, if you pass the enable line, that is R-L as 0, that we are going to perform the shift left. So you can also observe we have another input in the input LS, that is the last multiplexer or the D0 you are going to pass. You are going to start at left and move towards the right. Sorry, you are going to move towards the left, that is shift left. So from this I hope you understood the SISO left, right and bidirectional shift registers. I hope you understood this video. Thanks for watching up to now.